inverse function example, finding the inverse of a linear function. So in this example we are asked to consider a function f, y equals 2x plus 4, and in part A, on the same axis, graph function f and its inverse function f inverse. Okay, so to do that, let me copy the function. I will use a red color to work with the function f. So f is the function y equals 2x plus 4. So any points with coordinates x and y should be a point lying on the graph of the function. And since we know that it's a linear function, it should be a straight line. The straight line can be determined by just 2 points. So, but let us do more. We can work with 3 if we want, or whatever. So let me take some testing values here. So for x I can take 0, and if I take 0 for x, what I get for y is 2 times 0 is 0 plus 4 is 4. Therefore, the point with coordinates 0 and 4 should be on the graph. So this is the point 0 and 4. Okay, now let me choose another one. Let me take 1 for x. If I take 1, 2 times 1 is 2, plus 4 is 6. So therefore the point with coordinates 1 and 6, this one here, should be a point of the graph of the red function f, 1 and 6. Here it is. Let me take the third one, but it's not necessary. I have to say here very emphatically, it's not necessary to have more than 2 points, but let us do it anyway. Let me take the number -1 for x. If I take that, -1 times 2 is -2 plus 4 is positive 2. So the point with coordinates -1 and 2 should be on the graph of the function. Here it is, -1 and 2. Now the graph will pass through these points and will be a straight line, and we may work it, we may draw it shortly, but before that let us now consider the inverse of the function f inverse. Well, whatever the formula for the inverse is, what we know is that it should contain the points with coordinates which are interchanged. So there should be a point with coordinates 4 and 0 at the graph of the inverse, because it's corresponding to this point 0 and 4. Then there should be a point with coordinates 6 and 1 corresponding to 1 and 6 from the function f. And finally we should have a point with coordinates 2 and -1, which corresponds to -1 and 2 from the original function. So let me graph these points. So it should be 4 and 0. So this point here, 4 and 0, it corresponds to this one here. It's a reflection in the line y equals x. Then there should be the point 6 and 1. So it's like 6 and 1. It should be here. This one, 6 and 1. And it's corresponding to this one. Again, it is its reflection in this green line. And finally, 2 and -1. 2 and -1 is the point here, 2 and -1, and it's the reflection of this point. Now let me draw the lines of the graph. So the first graph should pass through these 3 points, and I can produce it a little bit to the left, like this. Okay, let me try to be as precise as possible, and let me make it a little bit thicker and stronger, and actually I can use the red color to represent it. So it's this line here. This graph represents the function f of x, so I may actually write it next to it. So this is the function f. And now let me do the second graph. So again I will need to draw a line which should pass through from this point here, and it should go like this. It should pass through the same intersection actually, and go to the left. Fine. Make it a little bit stronger and let it be blue. Okay, so here we are. This is the solution to the part A of the exercise. If we want, we may add arrowheads to these graphs to represent the idea that they continue in both directions without any restriction, like this. And you see that these graphs are reflections of each other in the line y equals x. Okay, so this is for part A. Now let's do part B. In part B, we are asked to find the inverse of x, first using the coordinate geometry and the gradient of the inverse obtained from the part A, and then the variable interchange. So let us do it both ways. The first way, in part 1 here, you can use it only in case of linear functions, because all the other functions have curved graphs, not straight ones, and therefore it won't work because their gradient changes. There is not just one gradient. But here we have just one gradient. However, the second method, the variable interchange method, is much better and it's more general. It works in any situation. So let us start with the first method. So it's the method part, let me call it 1 or I, whatever. Okay, so let us choose 2 points on the blue graph. So this is the graph of the blue function. This is the function f inverse. And let me choose this point, let me call it A, and this point, let me call it B. A has coordinates 4 and 0, and I write it here. So A has the coordinates of 4 and 0, and B has the coordinates of 6 and 1. Okay? Now, whatever point P I take on this line, which has the coordinates x and y in general, what is for sure is that the gradient of the segment AB has to be the same as the gradient of the segment AP. Gradient, to remind you, is the fraction. So let me write it. The gradient of AB, well, it is the fraction which is constructed as follows. First, take the difference in y coordinates between of these 2 points. So it's like 1 minus 0 here on the top, and divided by 6 minus 4. 6 minus 4. So the gradient of this segment AB must be 1 over 6 minus 4 is 2, so it's 1/2. Okay? And since A, B, and P are collinear, then also the gradient of AP must be 1/2, but at the same time, using the same definition of gradient, it has to be, if I write P below, which has the coordinates x and y, it has to be the fraction which has the difference in y coordinates between P and A, like y minus 0 in the numerator and x minus 4 in the denominator, x minus 4, like this. So then if I connect these two equations, 1/2 equals this, what I get is this one, and this should result in the equation of the line. So let me make some transformations. So first multiply by 2 and also times x minus 4. Okay, sorry for that, let me move it a little bit. X minus 4. So what I obtain is this, x minus 4 equals 2 times y. Now if I want y itself, I divide by 2 and swap the sides of the equation, and what I get is y equals x minus 4 divided by 2, or I can rewrite it, y equals 1/2 x minus 4 over 2, which is 2. And this should be the equation of the function f inverse. So this is the equation for the inverse function. Its gradient is 1/2, and its y-intercept, this should be the y-intercept, is -2. And you see really this has the intercept of -2 with the vertical axis and has the gradient of 1/2 because every time you move 1 to the right, you move at the same time 1/2 upwards to stay at the blue line. Okay, so this was the first method of obtaining the function formula for the inverse function using the coordinate geometry. And well, it may be a little bit harder for you since you may have forgotten already this stuff about gradients and so on. It's now perfect time to review this for the next lessons. Now let me do the second method. The second method of obtaining the equation of the inverse is very, very easy. So how it works? You take the equation of the original function y equals 2x plus 4 and you perform a very simple interchange. What you know is that once the point with coordinates x and y is on the function f, then the point with coordinates y and x has to be on the function f inverse. Therefore, if you interchange x and y in this equation, you should be okay. You should get the equation of the inverse function. So instead of y, I use x equals 2 times, and instead of x, I write y plus 4. So what happened here, I interchanged x and y, and what I obtained is a formula. But the trouble with this formula is that I have, well, x is expressed here, not y. So if I want to express y, I have to do some transformations. So first take away 4 from both sides, so subtract, it's x minus 4 equals 2y, and now divide by 2 to get y equals x minus 4 divided by 2, and again this can be transformed in the same way as before to y equals 1/2 x minus 4 divided by 2 is minus 2. So this is the formula for the inverse of the function f. This second method is much easier than the first one, I guess, and also it's more general. It can be used not only for linear functions but for all functions that you will encounter in this course. Okay, now let's do part C. Check that f composed with f inverse of x is the same as this and is equal to x. Okay, so let us do it here. First, I copy the functions f y equals 2x plus 4, okay, and f inverse is the function y equals 1/2 of x minus 2. Now what I need to show is that f, the composite function of f and f inverse of x is x. This is what I want to show. Okay, so to do it, I'll just rewrite this. So you may remember that this means f of f inverse of x, and this should be, then we start from the inner part, it's f of, now f inverse of x, well, you use this formula for the inverse function, is 1/2 x minus 2, and this equals, and then instead of f of this, you use the first formula and take this as the entire x value here, so it's like 2 times, instead of x I write this bracket, it's 1/2 x minus 2 plus 4. And now let us multiply. Well, it should be 2 times 1/2 x, it's x, 2 times minus 2 is minus 4 plus 4, and what you get is x. So this is really what we wanted to show, that if you combine or compose f and inverse of x, what you get is the identity function. It's the function y equals x. Now, to show it the other way around, we want to show that this combined with this composed, so we compose these two functions, composite function of inverse of f and f of x. We want to show that this is x again. To do it, we rewrite this using the more convenient notation. So this is the inverse of f, or f inverse of f of x, like this, and now use these formulae here for the functions. So first start with the inner part, so it's f inverse of, and instead of f of x I write 2x plus 4, so this is the formula for f of x, so 2x plus 4, okay, and now take this as a new value of x for the inverse here, so this equals, so it should be 1/2. Now instead of x I write 2x plus 4, and minus 2. So you see what you get. If you multiply it out, you get x plus 1/2 times 4 is 2 minus 2, which is again x. And this proves this fact in part C, that if you take the composite function of f and f inverse, it's the same as the composite function of f inverse and f, and it's identity function.